and welcome to another edition of the Super Spreader Seminar Series. So before we proceed further, I would like to acknowledge that the land of the network's head office is located on York University, and which recognizes that many indigenous nations have long-standing relationships with the territories upon which York University campuses are located that precede the establishment of York University. York University acknowledges its presence on the traditional territory of many indigenous nations with whom it has met several treaties. Regarding the Spreader Seminar series, this series is basically a run for and by the highly qualified personnel in the network, which includes the postdocs and the graduate students. It's basically a platform to present the research, promotion of ideas, and sharing of research experiences. And ultimately, we hope that we will be able to establish connections among the various highly qualified personals who participate in the several projects within this OMNI network. So today our speaker is Dr. Francois Viard. He's a research associate at the Faculty of Veterinary Medicine at the University of Montreal. He holds a PhD in mathematics and has several years of experience working as a developer and a data scientist. And currently his research focus is on the interface between mathematics, informatics, and epidemiology. And he has a strong interest in agent-based modeling and its applications for zoonotic disease investigations. So without further ado, I would like to share the screen with Dr. Viard. Thank you.
Sorry, I forgot to unmute myself. So I was saying, can you see first? Can you see my screen and my pointer?
Yes.
Okay, perfect. Because I may need to show a few things on the slide. So first of all, thank you very much for inviting me to talk. Today, I want to show you basically what has been my life for the past 3 years, I'd say. So it's a project that started initially as a side project before I went back to academia. Basically, a friend of mine, which is in Patrick Layton lab, had issues with some modeling problems and mainly performance issue. And I decided to help. And I started developing SamPy, which is a new Python library that is aimed at, its goal is to help researchers to develop agent-based model for the study of zoonotic diseases. So I started as a side project, then I became a postdoc in Patrick Layton lab, and we continued on the project, and I'm now research associate. And the project is at a stage in which we can share it to the world right now. So in this, it's not, okay. So this presentation will go as follows. So first, because I'm not absolutely sure everybody is at the same level in terms of what are the modeling techniques and etc. used in epidemiology, I will start with a very brief, very high level overview of some modeling techniques used in epidemiology. And then I will go into SamPy and talk about what it can do and give a few examples of the kind of things the library can do. Then I will go a bit more into the details of how SamPy works and how it's possible to actually go fast and make ABMs that go fast without using high performance computers, like using Compute Canada resources and stuff like that. And to finish, I will talk about what comes next in terms of this project, what's missing, what we want to add, and etc. etc. So let's start immediately with an overview of the modeling techniques in general. In general, it's always the same, let's say always the same principle when we want to model an epidemic. We have a system that can be described by a collection of variables. Like, to give an example, for instance, the system might be, we are in epidemiology, a population in which we unleash a new disease, and we want to see how this disease evolves in the population. In this case, the variable that could be used in classically would be, for instance, the number of people in the population that are infected, that are infectious, that are immune, and etc. All of these variables describe the system state. And it can be as simple as we want and as complex as we want. We can go as far into the list of variables that we want. And what makes it a dynamic system is that there is some form of transformation that actually tells you how you can turn the state at a given time t into the state at a time t plus some increment, some time step. And that's basically, each time we try to model the dynamic of an epidemics, we are doing this. The big one, like the first one that is generally used to do that in epidemiology, are compartment models. So in this case, in the simplest case, the system state would be just composed of some compartment that gives either the number of people in a population or the proportion of the population that are susceptible, exposed to the disease, infectious. And okay, here I wrote dead because I'm mainly working with rabies and there is no remission. But anyway, the dynamic part is generally given by differential equations. So ordinary differential equation, partial derivative equations, if you want to include some spatial components, for instance. Generally, those are deterministic model. Like those ODE, PDE are deterministic, but not always. You can find models that are using stochastic differential equations, for instance. And yeah, to finish, I mean, there is this trend that we are trying, because those models, I mean, at least in this form, are pretty, how can I say? I don't know how to say that in English. I mean, it's not very precise. There are a lot of assumptions behind. So currently, there is a trend to increase the number of compartments, for instance, include compartment by age and stuff like this, which can make those models actually fairly complex with a lot of differential equation going in all different compartments. The approach that I am focusing on in my research is the agent-based modeling techniques. So in this case, the system state is just, basically you can think of it as an Excel file, where each row of the Excel file is an agent, or represent an agent. That's the data that we have. And each cell on each row is contains some information, which is a characteristic of the agent. For instance, the first row might be its age. How old is the agent? The second is where it is, has it eaten yesterday, and etc., etc., etc. The dynamic in this case is not given by equations or stuff like this. It's generally given by a computer program that will take this huge Excel file and turn it into a new Excel file with all the modified characteristics. Generally, those models are probabilistic. I mean, we're trying to reproduce reality, let's say, that kind of system, but that's obviously not possible. So we make simplification, and one of them being when an agent decides to do something, it will take its decision based on some probability. And the piling up all those little random decisions by the agent, we obtain a very complex system that evolves over time probabilistically. And similarly as to the previous case, where the number of compartments is increasing, here we have a similar trend, but with the number of agents. We're considering larger and larger system in our ADMs. So now let's briefly talk about what's the good part about ADMs and why it's nice to work with ABM compared to compartment model, but not really. Those are really different. The first one that I really like, even if I come from mathematics myself, that it's easier to conceptualize without a mathematical background. What I mean by that is, like, even if I come from math, when I see a set of differential equations, personally, I have to sit down and take some time to think about what's going on. What does it mean? What each coefficient means? Why those agents are moving from those population is feeding this other compartment, and etc. etc. That's not really the case in ABM, because you can think of the agent as a simplified counterpart to the real stuff. For instance, if you want to modelize raccoons, you can think of each agent as a simplified raccoon living its life inside the computer. So it's easier to understand what's going on. Another part is that it's actually easier, so with some quotes, because there are some problems with ABM, but it's easier in principle to integrate complex ecological mechanism inside those models. I have an example in mind, actually, which would be if you're, for instance, studying some disease over a landscape, and you want to work with PDEs. So you make your model with your partial derivative equations and etc. And then you realize that sometimes the disease make jumps because, for instance, it may use birds or migratory birds that make huge thousands of kilometers jumps. And the disease can spread this way. It's hard to include that kind of things inside a PDE system. It's possible, but it's hard. In an agent-based model, that's simple. Just add a new agent that would be whatever bird is moving 1,000 kilometers in some direction. And the fact that we can, without too much thinking and work, include all those mechanisms, make that, in theory, what we obtain should be closer to the reality, let's say. So now the problem, the first one, the big one, is that developing a complex ABM, so the kind of ABM we need, is hard. It requires, so first, obviously, some computer science background. You need to know how to code, is to some level. And if you want something optimized, something that works well, etc. If, for instance, you want something big and you want to use high performance computer, you will need a lot of knowledge about how it works, how the computer works. And it's not the only problem. I mean, the other problem is that we need to have people that know about biology, know about ecology, that can, understand what's going on. If I choose to model something this way, what are the consequences on the model? It's a mess, so it's hard. In the end, another problem is that the program is often very complex, very complicated. And so hard to test, but specifically hard to trust, because I have actually one day someone told me that she considered that the ABMs were kind of black boxes, something that you can put whatever you want and it spit out results, but we can't really trust what's going on inside because it's so big, so complex that nobody knows. That's a big problem. That's a very, very big problem, in my opinion. And we need to be extremely careful in developing ABMs to have something that is somehow tested and that people can trust. And finally, the big one, the other big one, is the performance. As I said, there is a trend to increase the number of agents. And as the number of agents increases, the performance can become very problematic, right? Very, very slow. I will give a few examples in the following slides of what I mean by slow and how it can impact a project or even make the project impossible. So now let's talk about SamPy. My aim, so with SamPy, is to tackle those three problems. The first one, the big one, is performance. That's why I came into the project. I wanted to solve this issue specifically, performance. Ease of use was in my mind as well. Ease of use was in my mind as well. So it's designed this way. And the reliability is more like, because I come from the private sector. I mean, after my PhD, I went to the private sector. And in the private sector, testing and making sure everything works as intended is a very big part of a programmer life, work life, let's say. So that's what I aim to do with SamPy. The second part is that this library is so far heavily focused on epidemiological applications, and specifically on zoonotic diseases. But the structure of the library is actually quite flexible, and it will probably be generalized later to some other aspect of agent-based modeling. But so far, it's for epidemiology only. And tell you like a bit more, I said I started this as a side project because some friend of mine had problem with modeling. Initially, this library has been developed to replace something called the Ontario rabies models that I think at least some people here worked with, which is just a good model, but wasn't suitable for the kind of scale we had in mind in our lab. But during development process, actually the scope grew. It's not just a replacement for the Ontario rabies model anymore. But talking about the Ontario rabies model, let's look at that, which is one of the first successful application of SamPy, let's say, like the first big one. It's a work that has been presented in this series, I think, done by Dr. Emily Atchison. So big up backstory there. There is currently, I don't think it's over yet, there is currently an outbreak of rabies in raccoon in Southern Ontario. It started, I think, at the end of 2015. Emily will correct me if I'm wrong. At least that's when we detected the first cases. And obviously, because right on north of where the epidemic started, there is Toronto. Obviously, the Ministry of, I don't know which one, what's his name in English? Anyway, a Ministry of Natural Resources, I guess, decided to act and started to vaccinate everything to try to stop the epidemic, and particularly to block it from going north into the Toronto area. So this work here that Emily has done was to modelize the dynamic of the epidemic and compare the effect of various vaccination strategies based on all the real data that the ministry has provided us. I mean, it's been published recently. Basically, here you can see an example where no strategy is applied. If I believe that's the dynamic of rabies, each image being the average over a year of the new infection on the landscape. We see the wave motif going on. Just for an idea of the number of agents going on, at the start of the simulation here, we have approximately 1.2 million artificial raccoons living on this landscape. And here comes the problem that we had with the previous model. ORM works, it works fine, but it takes 10 days to run one simulation. And that's too much. That's really too much. I mean, during 10 days, your computer may crash. You may lose everything you've worked on. That's not possible. When you're working with ABM, there is also this part where you want to test things. You want to feel around with the parameters, try new contribution, et cetera, et cetera, et cetera. And if one test takes 10 days, you will never see the end of the project. And you will never have enough simulation. You will never be sure that you tested enough things. And so the comparison is with SamPy, one run takes 15 minutes and use a single CPU, which is, so I think at least 2 orders of magnitude faster, but I think a bit more, nearly 3 orders of magnitude. So that's quite an increase in performance. And it turned the whole project from being very hard to do to actually doable. So performance matters. And if you're curious, I think Emily did in her paper some analysis showing that it's actually behaving as expected. Like, for instance, that we have the same kind of result that the entire rabies model had, and ORM has been tested thoroughly. So another kind of application, I mean, moving from there, that was the initial aim for the library. Moving from there, we started to use SamPy for other things. So that's an ongoing project. So with PhD candidate Norma Forero, the idea is to study spillover mechanics. So we are at a very early phase studies to have several species living on the landscape, and we are having a disease that can propagate between the species. So to give you an idea of what's going on here, we have two species, mostly biologically identical, living on the same landscape, sharing the same kind of resources. So it's just basically it's just to see if everything works. And I made some animation for that. If you want to know what's going on, here's an animation. So at this time, we have the weekly dynamic. Each frame is a week. And so what's going on here is that we have a disease that starts within species one, that propagates within species one. This disease can jump from species one to species two, which is on the right, and it can propagate within species two, but there is no jump from two to one. And we can see on the dynamic that everything we see basically makes sense, is that the species two endure some pressure, let's say, from species one. Species one has its own independent dynamic, but each infected agent in species one can infect an agent in species two, so the disease spreads further in species two. So that's the kind of things, and we're working on that on this project. The ultimate goal here, at least for this project, would be to model skunks and raccoons, because in the Ontario case, actually the disease jumped to skunks, and we have cases in skunks. So if we want to modelize more finely what's going on in Ontario, we need to include skunks. And that's the end goal of this project. And finally, another one, like, it's an application to another kind of rabies. I mean, for the moment, we mainly focused on rabies. So it's a work that's being done by another PhD candidate, Agatha Libert. This work is to study Arctic rabies, whose main reservoir is the Arctic foxes. I don't have nice animation for this one, basically, but the idea behind was is to study how the distribution of resources, and specifically how resources may vary over time, can influence the rabies dynamic. And here we have an example. I mean, those are the kind of landscapes she was considering in the study, with uniform distribution of resource, some discrepancy in the distribution, and one where the resource vary over time. And this was an extremely big simulation. It's basically a huge sensitivity analysis to try to figure out which are the parameters that influence the most the rabies dynamics, the Arctic rabies dynamics, because we have a lot of unknown there. I mean, Arctic rabies, the problem is in the name, Arctic. How do you get data here? I mean, and that's a problem. And so there are many mysteries about the dynamic of Arctic rabies, and many hypotheses of why it's maintained, despite the fact that the population density is extremely low up there. So yeah, the sensitivity analysis ended up being like 52,000 simulations. That's a lot, because each simulation is big and there is a lot of agents going on. I mean, at least until rabies is unleashed. When rabies is unleashed, it's kind of cleaning the plate. And the paper is mostly finished. We are editing the last bits, and it should be submitted in the following weeks. And this work has many potential follow-up papers. So that's the kind of things we are working with. in the following weeks, in the what I'm saying, in the past years. So, okay. Now I'm done with kind of talking about the examples, what SamPy can do, and the fact that it can go fast, and why performance matters. Now I want to go a little bit deeper into the detail of why SamPy goes fast. So before I go into that, please note that there is some level of simplification going on. I will talk about how, in general, frameworks deal with memory and etc., and deal with the computation. But keep in mind that this is a simplification. There are a lot of ABM frameworks. Each one of them is doing its own things in its own way. So there is no generality here, and you can have pretty huge difference depending on which framework you use in which context. But I will try to give you an idea of what's going on and why I took a different approach with SamPy and why it goes fast. So first of all, let's look at if you remember what I showed in the previous slide about the dynamic, where we have let's say a state, a system state, and something that actually modify the state to get the next step. So on the left here, we have the RAM, which is the working memory of the computer. I won't talk about the hard drive because that's not our concern for simulations. So the RAM is where the computer stores things that it needs access to regularly. So in the RAM, basically, in an agent-based model, we have agents that are stored as objects. So I won't explain what objects really are in programming because that's a whole course, basically. But we can think of it this way. The RAM is like a very long ribbon of memory slots, so little square. And an agent inside this is a sequence of square, like a blob of squares of memory slots in which informations are stored, and those information describe the agent. Here I took something simple. We have only three kind of we have three variables describing what's going on in the agent. And each agent is a blob somewhere in the RAM. Now, so this is the state of the system. And what changed the state to get the state at the next time step is first the CPU, which will do the heavy lifting, and what we call the activation scheme. That's the program. That's the sequence of instruction that the program will follow to make the system evolve over time. So here, I took the activation scheme that is the most commonly seen for one very simple reason. It's the default one in NetLogo, and most people just use that. So how does it work? That's pretty simple. First, the CPU will get an agent. So here I'm taking them in order, but in general, the order is randomized. But here we will do it in order. So first, it gets an agent. What does it mean? Is that the CPU has its own memory just near it. It's called the cache memory. And that's a very, very, very fast kind of memory, but very expensive and very, it generates a lot of heat and etc. So you can't replace RAM with cache memory. That's never gonna happen. So it loads basically at once the whole blob of agent one into the cache. That's the first step. Then it performs the action. So here, to make it simple, decided that action one only cares about the first orange variable, action two only change something on the purple one, action three on the blue. It's to make it simple. Actually, it could be more complex. Maybe the action needs information that comes from somewhere else. There are lots of things. Once this is done, in the CPU, once the CPU has finished its job, basically what you have to imagine is that what's going on in the cache is that we have a modified version of agent one that differ from what's going on in the RAM, because the RAM has not been modified yet. And so the next step for the CPU, and that's where actually there is room for variation between frameworks, because this can be done in many different ways, and it largely depends on how the frameworks organize its memory. But for simplicity, let's say that's what's happened there. The agent is pushed back into the RAM. Result is stored in the RAM. And that's where the problem comes. Each time the CPU deals with an agent or a few agents, it has to talk with the RAM. And RAM memory is slow. Random access memory is really slow. It's 1,000 times slower than CPU. So that's what we call a memory-bound program. That's the speed of memory that limits the speed of the whole program. And there is no foresee, I mean, we can't see any movement in the industry or anything indicating that the RAM is going to become any faster. Like maybe there is some breakthrough going on in some lab, but we have no idea. So basically, memory bound equals 1,000 times slower. And since those programs are generally memory bounded, it means that the choice of the language generally does not matter much. It would be a bit complex to explain, but if you start to use C or C++, basically what you're unlocking is the potential of the CPU, the potential to compute very, very fast. But if what's limiting you is the speed of the RAM, the fact that you can use your CPU fast doesn't change anything. So writing an AVM using Python or using C in this setting wouldn't differ much. So how can we solve that? So one of the solutions to the speed problem is actually the high performance computer road. It's to use a lot of CPUs. Each CPU load an agent and perform the action and then push back the result. As I'm saying on the left, this with quotes because it's needed, it has some issues. One of them being the complexity. The program in the end are way more complex, but it has also some, how can I say that, technical difficulties that come, like maybe they need to share resources. Maybe the CPU need to talk to each other because they need information from each other. And so you have all these new layers of having those CPU that needs to talk to each other to take care of. So the program that was already complex becomes even more complicated. That's a road. You have frameworks that do that. That works nicely, but it comes with problems and it's not for everyone. So here with SamPy, we took a different approach. Let's say a kind of radical one, because we decided, so I won't go into the detail, but we decided to get rid of at least some of this object-oriented paradigm. Not completely, obviously not, just that the agents are as object has been gotten rid of. Basically, the first thing we did was to reorganize memory. Now, before where we had agents organized in blob, now we group together all the characteristics and variables of the agents in long contiguous, which is technically important, arrays of parameters. And if you want to get, for instance, agent 1, here you need to take the first element of each one of those attributes array. So at first glance, it's just like, okay, if we do that, like, why not do that? The end result, if we let it as is even worse than before, by far. Because in this case, if the CPU wants to load agent 1, it has to go get data from here, wait for the RAM to be available again, get data from the second one, and get data from there. So actually, with this setting, we have more memory calls. So we made the problem worse by far. So we need to change something else. And that's where the, let's say, the nice solution comes, and it has a lot of very nice consequences, that if we change the activation scheme on the right. That's what we change. And we do this. So that's a different activation scheme. The ABMs you obtain are different using this approach because modifying the activation scheme modify the ABM. In this new setting, instead of getting the agent one by one, we are treating the actions one by one. So here, for instance, we will start with action 1. We shuffle the order of the agent if needed, if it makes something, if it impacts the result. And we have each agent perform action 1. And then we move to action 2, and then we move to action 3. Why is it a good thing? It's because CPUs are designed to work with that kind of things. Like CPUs are designed to, when they ask something to the RAM, they don't just take what they asked for. They receive a whole lot of other data that came after. And it means that's a design. It's been designed this way to overcome this problem of the RAM being slower. So it means that if you want to basically unlock the power of your CPU, you have to group all the data together so that one memory call gets a lot of data. There are other optimization things going on here, but that's the big one. And it's even more than that. I mean, a part of the CPU is actually devoted to specific tasks like anticipating what the CPU will need. It's called the memory manager. And it works really nicely with really simple arrays. And that's what we have. We have very simple arrays. We don't have like, we could work with arrays of agents, but those are complex and et cetera, et cetera. Here, we keep everything simple so that the CPU is at home, feels at home, and knows how to optimize that. And that's how SamPy unlocks speed. That's how we get huge speed increase, because doing this, we reduce the burden of the memory bound thing. We still have some problem with memory, but not as much as before. And as I was mentioning, the RAM is approximately 1,000 times slower than the CPU. And that's the kind, I mean, a bit less, like we see increasing performance compared to ORM that are like 100 times faster at least. And that's expected because we kind of overcome the memory bound problem. So what are the benefits of the approach? I mean, as I was saying, it's fast. But one interesting aspect that was not, let's say, not completely planned, my part, is that actually working with this and having these activation schemes where actions are performed in seconds leads to very easy to read and understand scripts. So here I have the only piece of code in this whole presentation, which I hope you can read, because now that I look at it, it's really small. Basically, if you look at the script, you know what's going on. So here I have just a little piece of some, I think, toy example involving raccoons. Here you have like the main loop. It's the loop. Here, basically, we're saying, okay, we loop over all the weeks of the number of years we want our simulation to last. And then we list all the actions. And that's what's happening. First, the raccoons kill to hold. That means that whatever is to hold, whatever raccoons has crossed this age is killed. Then new action. So this natural death ORM methodology is a way, it's a reproduction of something found in ORM to modelize natural mortality of the agents. So that's what's happening. That's the second action, that agents dying of natural cause, and et cetera, et cetera. And you just read the script and you see the list of actions going on. So that's kind of answer the problem of scripts being hard to read and ABM being hard to understand. It's that actually you can open the script and read. There is nothing hidden in the sense that you don't have this framework that take the stuff that may shuffle the order of actions that may, no, it's very simple. It's written in the script and that's all there is. Another benefit is that each one of those actions can be optimized. So I mean, what the first idea was to go fast. So everything is optimized and it's tested. So that's the thing. It's like if you want to create your ABM using SamPy, you take SamPy, you take the library, and you construct your ABM using actions that SamPy make available to you. And each one of those actions has been tested. So as long as you're not doing something completely random with the parameters, it should work as you intend it to work. And there are some safeguards about the parameters, but that's another topic. And yeah, the last point, I mean, it's fast, made to be fast. And interestingly, it's mono-threaded. So what does it mean is that it uses, if you write a script and start it, actually made sure that it's always using a single CPU. Why does that matter? Is because in our epidemiological setting, what we really want to do is to start thousands of simulations. We are not really interested in having one that is perfect, because our parameters are always blurry and kind of crappy, and we don't know which one should go where. So we want to start a lot with a lot of variation of the parameters to see all the possible outcomes. So by doing this, by making sure that it only uses one CPU, I make sure that if on your machine you start 10 simulations in parallel, those 10 simulations won't try to compete with each other for resources. They all have their CPU, and that's it. I mean, they will compete because that's how computer works, but it's not, this competition will not be caused by the program itself. So to finish, what comes next? So as I said, it's a library, so it gives you a set of tools to build your ABM. So to create your populations, to have actions that your agents can do, to have disease, to have intervention, to have landscape, and et cetera, et cetera. And the first thing is like right now, it's mainly, all those actions are mainly focused on rabies application. And we need to make the list of possible functionalities larger. One of which being new kind of actions to modelize other animals, for instance, birds, and many new disease types. Want to add vector-borne diseases, starting with ticks. Another point, we want to add more tests because there's never enough tests. We need to test more and more and more. Now, a big problem that I see right now, that there is a problem with onboarding of new user. I mean, the code itself is fully documented. Inside the code, you can find explanation of the technical part, like, okay, how it works, why it works, what are the parameters, etc. Everything is in the code, but it's very technical, and there is no, so far, high-level introduction. Like, okay, what's the philosophy? What's going on with SamPy? How you should think about the problem and organize what you should test and see and check to see if SamPy approach actually fits your problem. All that is missing. So it's rough. Basically, yeah, these need to change. And probably that's, I don't think I will start right now, but that's probably what will happen soon, is that there will be a website with those tutorials and introduction and etc., as well as the documentation that will be taken outside from the code and put into a website. So that's it for me, I think.
Awesome. Thank you so much for the presentation. So we do have some questions in the Zoom chat box. So the first question is, what is the difference between the agent-based modeling in Python called AgentPy and your program SamPy? Are these the same or function differently? Another related question is what influenced the choice of the name of the library as SamPy?
So for AgentPy, I don't know AgentPy precisely. The big one, the big modeling library I know is Mezza in the Python ecosystem. So I'm very curious to look at that, and I will give it a look right after the talk. And the choice of the name SamPy is because, so actually it causes a problem because there is a project called SamPy related to some astronomical communication of devices. I mean, it's too bad. The choice was bad, but yeah, that's it. And the name is just because it's short and it kind of rhymes with other scientific library names like NumPy, SciPy, and stuff like this. So SamPy fits. And so it means stochastic agent modeling with Python.
Okay. So next question is, what library or framework was used for the original rabies model?
So for the Ontario rabies model, the very first version was in the very first, yeah. I forgot the name of the language. My God, sorry, I'm a bit tired. Not C++, not C, something else, something used by physicists a lot. Oh, sorry, I forgot the name of the language. Something old.
Is it
70s.
Rust?
Huh?
Rust.
No, Rust is recent. I would have loved it to be written in Rust. No, sorry, but the current version has been rewritten and it's in C# right now. And it's not relying on any framework. They built everything from the ground up.
So the next question is, were the core calculations still in C? I guess that's the same question as a programming language. Next question is, how easy is this to use if you have no Python background? What would you recommend for people interested in trying to use this for their work?
If you have no Python background, there is a need for, okay. That's also why I was talking about onboarding, and that's really something missing. And I don't have a real visibility of what it means for someone that has no Python background to start with that. And if you want, there is an ecosystem of scientific libraries, NumPy, SciPy, and all these things within the Python ecosystem that are relatively easy to use. And I took a lot of inspiration from them. I want SamPy to feel like those libraries. So it's as easy as NumPy and SciPy, but still it requires some knowledge and knowing a bit of Python before using those libraries. So SamPy as well, I would say. So yeah, you need to have some introductory class, I guess.
So I mean, another question that I have and is related to that is, so when you were talking of the website and the network, do you also like want to make a, plug and play kind of version for people who are interested in epidemiological models but do not have that Python background? Like, would that be something that you would be interested in, or someone in your group?
So that's something in the list of things, but not in the immediate future. That's something in the list. There is a need for that. But not while I'm alone on those projects. If some other people are coming into that, yeah, it would be nice. And I've seen in the chat people mentioning Fortran. Yes, that's Fortran. Sorry, I completely forgot the name.
Okay, last question I think is, have you incorporated government, public policies and individual behavior models or behavioral responses to policies into the models reported in your library?
Not really, because the focus have really been on zoonotic diseases and nothing about human epidemiology so far. So basically they eat baits when we vaccinate them. That's it. So yeah, that's not included yet.
Okay, Piyush has a question about, do you accept people for contributing to the package? Is there any forum or channel you use to communicate?
So that's so I had, there is a GitHub and it's open. I mean, it's an open source project. Okay, so it's an open source project, so everybody is welcome. But so far I've been alone on that, so nothing is set in stone yet as how this would be organized, but everybody's welcome. Like, shoot me a mail and we will talk about that.
And I guess this is the whole idea of setting up this kind of presentations with the HQPs involved. So that's the importance of the seminar series, is to enhance the collaboration. So if anybody is interested, you can shoot Francois an email. The next question is, epidemiological models are changing over time, and how the library could be updated regarding the progress in the models. And I guess that also adds to, you need more people, I guess.
So that's so the way I had to design. Okay, when I started working on this project, it was, and especially when I started the postdoc part, and it was not just a side project anymore. It became very clear very fast that these had to be flexible, like really flexible, because we have module to add from every direction for many possibilities. So it's designed to be flexible. Basically, it has a, how could I say, ECS organization, entity component system, kind of thing. I mean, I took inspiration from stuff in video games development and lots of things, but it has an organization that allows, by composition, kind of, to add new blocks inside the codes and change stuff. I don't know how far it can go, because I suspect that this kind of organization will be quite a burden on the lead developer part stuff, because you have to keep everything organized. But so far it works. So I hope it can be modified for a while, but as any project, I mean, at some point it will become too large and need to be changed. But yeah, it should be able to follow for a few years at least.
Okay. So the next question is, are there any funds to support modeling? So Murtaza is interested in working on public health mathematics integrated into ABMs. I guess that's a question for higher ups, but if you have any suggestions.
I don't know. I guess so, because there is some interest from many people for that kind of project. But I'm just getting back into the academic and research thing, and we had COVID, which kind of, blew everything apart. So I guess so, but I don't know. You should probably ask other more senior researcher on this question, but I think so.
Awesome. So I do not see any more questions or hands being raised. So with that, I would like to thank Dr. Viard for the presentation, and I would like to thank all the audience members for their participation. Thank you and have a good day.
Thank you.